As of October 2023, there are around a dozen mature PostgreSQL libraries, all level of abstractions, from low-level queries to the type level. More than enough for anybody. So shout out to everybody who says that Haskell has no libraries. Which one to use? Let's see. For each library, we'll talk about features and basics like writing queries, complexity, pitfalls, everybody's favorite topic, errors, and so on. Throughout the tutorial, we'll assume that you're familiar with fundamentals of SQL and PostgresSQL. Before integrating it with the database, let's discuss the data and the setup. Let's imagine that we are building a tiny warehouse management system. A warehouse has multiple products, some quantity of each. Product has a label and a description. Description is optional. Product can belong to multiple categories, so we have a many-to-many relationship. And category has a label. In the repo, we have a script, and we also have a schema. And this is a generated visualization of the script. This part is optional, you can skip ahead, but if you're interested and want to follow along at home, this is a few things that you need to know. And first thing, if you don't care, don't like Docker, or already have an easily accessible PostgreSQL server, feel free to skip this section as well. So first, install Docker. Then do docker compose app, depending on your version, to start the PostgreSQL server. You can see what it does in the docker compose YAML file. It initializes the database and tables using the script we just saw before. It mounts the data to the Postgres data. In case you need to do something with it, you know where to find it. And there are some hard-coded things that the code relies on. You can find these values in the hard-coded module in the code for laziness reasons. And this is the base of it. For some reason, you need to connect to the container and run arbitrary queries using psql. Here's the command to do it. And note that this part is a container name, which might be different for you, probably. You should check with Docker PS to get the right container ID or name. We also pass a couple of flags for username and database name, so your mileage may vary. As I mentioned before, we start the server with docker compose up, and eventually you do docker compose down to stop and remove the containers. If you have stack installed, stack build to build, and stack run to run, that's all you need. We use LTS 21.7, which comes with GHC 945. And published somewhere mid-August of 2023. Note that most of the libraries rely on using various extensions. And here's a quick overview of the most important ones. Overloaded strings used to simplify the constructions of query values. We can use literal strings like select all from user instead of manually constructing the whole type. For example, in the case of postgresql-simple, we would have to wrap it in string UTF-8, convert it to byte string, and then wrap it in a query. With extensions, we don't have to do that. Template Haskell is fairly useful for generating boilerplate code. Some libraries provide the template Haskell machinery to derive type class instances and also generate custom type-safe data types at compile time. Derive any class and derive generic enable alternative ways to get free type class instances. On top of that, we'll use deriving strategies to make the deriving explicit. For instance, in the following example, we have a category data type where we derive generic instance and then use it to get to row and from row for free. Some libraries, like postgresql-simple, provide quasi-quarters for less tedious SQL construction in Haskell code, like in the following example. Only one Postgres library requires duplicate record field extensions to function, but it's also a stylistic choice. We use this extension because we have multiple data types with a label field, which is not allowed otherwise. We're going to use overloaded record dot extensions to access record fields as well as specific columns of the tables. For example, you can say product.label. And note that the project itself uses GC 2021, which includes derived generics, type applications, and many other extensions required for some libraries to work. So if you cannot find them declared explicitly in the module or in the project, it means they're included here. Also, for the tutorial sake, we'll use the included in GC 2021 scope type variable extensions to demonstrate some intermediate types. Let's start simple. PostgreSQL-simple describes itself as a mid-level PostgreSQL client library. In other words, we'll write raw SQL queries and the library will deal with the security and stuff. To get started, we add PostgreSQL-simple to dependencies. We're using version 0.700 published in 2023. First thing we need to do is to connect to the database. We use connect to acquire a connection. It accepts connection info, which we can get by using the default connection info and override some defaults. I mentioned the hard-coded module before, which has all the required info, host, database, user, password, and so on. Eventually, we'll have to close this connection after we use it everywhere. But you'll probably not need to do it manually. This is just an example to get us started because you can use withConnect and bracket or better connection pool. All of this function is going to take better care of the connection and making sure that in case of any failure, the connection is getting properly closed. The library doesn't support connection pooling, but you can use the resource pool package or something similar. So how do we modify data? We use execute and execute underscore to insert, update, or delete data. This version with underscore suffix is simpler. It doesn't perform any query substitution. We can use it with hard-coded values or with straightforward queries such as truncating the tables. And this is the first thing we want to do, just drop all the data. Both execute functions return the number of affected rows, which is not relevant in case of truncate because it's 0, right? And safe to ignore. So we use void function that explicitly ignores the result of evaluation and returns a unit. We can use execute to make a proper insert and pass some values for substitution. The simplest way is to pass a tuple of stuff. For example, in this case, we pass a label and a description. And sometimes we have to be explicit about types. For example, in cases like this, where we have string literals and overloaded strings enabled, or when we use numeric literals like 244, we have to help the compiler to figure out is it an integer or float or whatever. Because there is no tuple of 1, the library provides a custom type only. So when we want to pass just a label without optional description, we have to wrap it in this only type. Alternatively, we can use list. And in cases like this, we pass a list of one element, which is still a valid list, right? But preferably we use types. We declare a basic product, which takes a label and optional description. A record can be turned into a list of substitutions with a to-row type class, which is derivable using GHC generics. First we derive generic, and then we derive to-row and from row. And if we want to modify multiple rows, we can use execute many. And in this case, we pass a list of categories. Execute returns an IO, so we can easily get the connection, insert all the stuff, and print it out to see that everything is working. The execute functions cannot return any results, other than the number of affected rows as we've seen. We have to use the query functions. Similar to execute underscore, query underscore takes a query with no substitutes. So we can use the simplest query to showcase this. We select ID, label, description from the product table. And note that we must be explicit about return types. The library cannot guess what we want. In this case, we expect ID of type int64, which responds to the serial, required text label, and optional description. But we can also specify a record return type. If we derive from row, recall that we already did this. For example, we can return basic product, the one that has label and description, and no IDs, and filter for the label by passing one parameter, which is in this case this specific crew kit, wrapped in only because, as a reminder, there is no tuple of 1. If we want to, we can use the in clause, and the library provides a dedicated wrapper for the in clause. And we can verify that everything is working. In the first case, we got all the 4 products that we inserted with all the random IDs. In the second case, we asked and received the specific kit number 2. And in the last case, we got 2 kits, the 2 and the 3. Now imagine we want to atomically insert a new listing, product, category, and quantity. This touches multiple tables and requires a transaction. Additionally, because we have a many-to-many relationship, we have to insert product and category first, and then use their new IDs to create a mapping. We can use returning to get IDs of created rows. First, we insert a product and get the ID back. Then we insert a category and get the ID back as well. And note that we have to use query here and not execute because these queries return results. And then we get these IDs, insert them in the warehouse table and into the mapping table. In case something went wrong because the library doesn't guarantee the IDs are going to be returned, doesn't guarantee there's going to be one ID back or multiple ones or 0 IDs, we throw a random error saying that, okay, something failed. On top of all of this, we use with transaction to wrap multiple queries in a transaction. Any error will roll back the transaction and the exception will be rethrown. In this example, we throw an explicit error if we don't get the expected IDs for some reason. Note that in case of SQL error, the exception will not only roll back the transaction, but if uncaught, will propagate further, killing everything on its way and potentially crashing the whole app. So we should at least wrap transactions in exception handlers. We'll see how to do this later. And when you need to, you can also use granular transaction functions like begin, commit, and roll back. In our case, it's all boring and there are no errors yet. So if we want to see what we inserted, we have to read all the tables at once. We need to query using a few joins. The library provides a quasi-quoter that makes writing big queries easier. We can format the query and don't worry about the white spaces. To get all the data we To get all the data we want, we join the warehouse table and product based on the product ID. And then if we want to get all the categories for the product, we have to do 2 outer joins because we have a many-to-many relationship through the intermediate table. And to make it just tiny bit more interesting, we filter for the quantity where the quantity is more than 3. Because we just inserted this, we get back the screw set with the quantity and the category, as expected. In postgresql-simple, all the programmer errors in SQL or library usage are runtime exceptions. If the query string is not formatted correctly, we get format error. For instance, if we have a mismatch in the number of substitutions, the question marks, and the actual values, the stuff that we pass. For example, in this case, we're passing 2 strings, but only expecting 1 parameter. We get this wrong query formatting error. To handle the error, we use handle function, explicitly state which kind of error we want to handle. The error handler, in this case, we just say, okay, it's boring, we want to catch and print the error by displaying the message and the exception itself, and pass the action. In our case, we also use void because we don't really care about the output, we just want to see errors in action. And we have similar situation on the return side. If the number of columns doesn't match the number of elements in the result type in the list tuple or record, we get result error. The most likely variants are incompatible and unexpected null. In the first case, we return an optional description, but we type it as required text and it fails. In the second case, we return ID, which is just an integer, and we type it as a basic product, and it also fails. On top of that, if we misuse the library by mistaking query for execute or vice versa, we get query error. For example, if we use execute with insert query that has returning, we get a query error because we were supposed to use the query function. And the last but not least, any SQL errors from PostgreSQL will come back as a SQL error. For example, if we make a syntax error, write some gibberish, or violate a constraint, we get a SQL error. What about learning resources? The docs are simple as well. Library covers all the basic examples, describes the functions, and provides a couple of examples. Outside, there are a few blog posts that cover similar things, mostly targeting beginners. And you don't need more than that. If you know how to write one simple query, you know how to write them all. The library has a companion postgresql-simple migration library, which has been archived since 2021. What does it mean? I don't know. So overall, PostgreSQL-simple is a library for all levels and great option if you love writing SQL by hand and don't need reusability. It doesn't parse or validate the queries, so we have to pay attention to what we write, to the SQL queries, Haskell types, the order of parameters, and so on. The next obvious step is to add more type safety. According to README, hasql is a highly efficient PostgreSQL driver for Haskell with a type-safe yet flexible mapping API. It's production-ready, actively maintained, and the API is pretty stable. It's used by many companies and most notably by Postgres project. Haskell is a ecosystem of libraries. To keep it simple, let's limit ourselves to hasql, hasql transactions, and hasql's template Haskell. We're using hasql 1632, published in 2023. We will also use vector, contravariant extras, profunctors, and tuple packages to make a few things tidier. This is not required and it's all about copy-paste anyways. It's not very important, but we assume that you've seen the part on PostgreSQL-simple from before, which covers the same topics but in a slower pace. Okay, first we get a connection. Note that acquire returns an either connection error or a connection. But for now, we're just getting started, so let's pattern match and don't worry about possible errors. We'll deal with them later. In reality or production, you should probably use hasql pool to work with a pool of connections, not a single connection. Let's start with the cleanup again and see all the main players. Session is a batch of actions to be executed in the context of a connection. Statement is a specification of a strictly single statement query, which can be parameterized and prepared. You can think of it as how to make a query. Statement consists of the SQL template, parameter encoder, result decoder, and a flag that determines whether it's prepared statement or not. And then run executes a bunch of commands or statements on the provided connection. And remember that you can see the complete code in the repo if you need to. We have a simple query with no parameters and no result, so we don't need to encode anything or decode anything. That is why we pass encoder for no params and decoder for no result. If we want to pass parameters, we need to supply decoder. First option, tuples of primitive types and manually written decoders. Imagine we have a insert product SQL, where we need to pass a label and a description. We pass row params, which is encoder for our parameters. We use countermap operator and append operator to compose multiple parameters. What we want to say is that the first one is non-nullable text, and the second one is a nullable text. The rest is just glue code and boilerplate. The rows affected decoder is a decoder for the result when we want to return a number of affected rows, which is going to be an integer 64. Note here that instead of first and second and all of this, you can use contrazip family of functions from the contravariant extras package to reduce the boilerplate. So we put it all into one statement, and then we run the statement by passing it a tuple. Here we build one session that inserts all the products and all the categories that we want, and returns a single sum of all the rows affected, and then we execute it with run on a specific connection. We'll see it after we view all the statements. Another option is using records. In this case, we still provide an encoder for the parameters, but instead of using first and second to work with tuples, we use field selectors to select a label and a description, and once again say which type they map to, and is it nullable or not nullable. And we run it in the same way. If we want to modify multiple rows, we have to use Postgres unnest function. There is no special support for inserting many things as in other libraries. Note that using unnest is more efficient than executing a single row insert statement multiple times. The category params is an encoder that allows us to pass a vector of categories to insert. First, we specify how to encode the elements of array, and then how to encode the whole array to get for the vector of category. And as I mentioned before, we combine all of the insert statements into one session by summing and return the sum of all the affected rows. In this case, it's 5, 2 products and 3 categories. Querying data is not that different. We need to provide encoders for the parameters, in this case no params, and the decoder for the result, to specify how each row result maps into expected type. So we have non-nullable int 64, non-nullable text, and nullable maybe text. If this sounds tedious, we can ask template Haskell to do the work for us. In this case, we use singleton statement that expects one result. There are other variants we'll see later. We write the query and specify the types, and SQL template Haskell handles the encoders and decoders for us. But if we want to use custom types instead of tuples, we still need to handle the conversions. The result of the statement has a profunctor instance, which allows us to modify input parameters and output results. In other words, we need lmap to map parameters, rmap, which we use in this case to map results, and dimap or dimap to modify both. For example, if we want to return basic product, we modify the result with rmap. We use fmap and unquery-n, which is specific function from the tuple package, to convert the tuple into basic product. If you don't want to use tuple, this is pretty much just taking some result and manually mapping A to A and B to B in the result. And why do we have nested fmap of result? It's because we're using maybe statement in this case. We cannot use singleton statement because there is no guarantees that we're going to find something with this where clause. So we use maybe statement and get a maybe result. We can also use vector statement to return an array of results. Hasql doesn't have a special support for an array as a parameter for the in operator. We should just use any from Postgres. Similar to the previous example, we pass a list or a vector of labels, use it in the where clause, return the tuple which we map to basic product as we've seen before. Then we convert every statement into session. Every session we run, get the result, and print it to the console. The first query returned all the 2 products that we inserted as tuples. The second statement, we use the template Haskell and return the tuple of the label and the optional description. In third example, we return maybe of the product, which has label and description. And the fourth example, we return 2 products using the in clause. We returned a vector of products. In this case, there was 2 products included in the in clause. And notice that in all the cases, list and maybes and concrete types all wrapped in the right data type. We'll talk about this later. We can use returning to get IDs of created rows. For example, to get back the ID of inserted product and to get back the ID of inserted category. Both of them are single statement because we assume if we put one thing, we get one thing back. To wrap multiple queries in transaction, we can use hasql transaction. First, we compose the statements, this time using different statement function, the one that comes from the transaction module. We insert product and get ID back, insert category, get the ID back, and then use these IDs to insert the stuff into the warehouse table and then into the mapping table. And at the end, we return the number of IDs. Note that if we don't care the result of the statement, we can use resultless statement, which is gonna give us unit back. And if we wanna get the affected rows back, we can use rows affected statement like we do here. And then we run the transaction using the relevant isolation label and mode on some connection. We can query these tables using a few joins. There should be nothing unexpected here. We do the same few joins, return the vector statement, map the tuple into the listing, don't forget to specify all the types, and filter for the quantity using specified parameter. Then we run the statement on the given connection and get back the result, which is a listing with a given quantity, label, description, and a category that we just inserted. We've been neglecting this until now, but as you can see, all error reporting is explicit and is presented using either. And just as a reminder, don't ignore errors and don't pattern match only on write, because the pattern match failures are very vague. The other good thing is that the hasql template Haskell parser is pretty good at error reporting and catching typos at compile time. And most of the time it's more explicit than what you get from Postgres. Also, the library does not accept or does not compile if you forget to specify one of the types. For instance, if you omit the type from the label, we get a somewhat generic error saying that there's a missing typecast. This also ensures that most of the input and result type, including nullability mismatches, are caught in the compile time. For example, if we forget an input type or return a wrong result type, we get some sort of mismatch. However, we are not safe from the programming errors. We should use correct statement functions not to get a runtime error. For example, if we use singleton statement for the statements that might not return a result, instead of maybe statement, we get an error, which says that there was an unexpected amount of rows. Or if we use singleton statement with unit result instead of resultless statement, we get an error saying that unexpected result, it says okay. And in case of runtime SQL errors, such as violating the constraint, we get a similar error, which contains an error with the SQL, with all the parameters we passed, and the error from Postgres. Core README has good overview and example. The library has simple documentation, a couple of tutorials, and a few talks from the author. hasql migration tool is a port of postgresql-simple migration for use with hasql. Overall, hasql is a great choice if you want to write raw SQL queries with more type safety and compile time syntax checks. The ecosystem comes with other whistles like pooling and transaction, and the template Haskell module with compilation time checks are optional. If you want, you can deal with the encoders and decoders yourself. The library requires basic knowledge of Haskell ecosystem. To be comfortable and productive, you have to be familiar with vectors, country-variant functors, and so on. Other than that, the library is quite straightforward. If that was not enough, it's time to move to the type level. According to README, persistence goal is to catch every possible error, and it comes close to that. It's also designed to be adaptable to any data store. As a result, a major limitation for SQL databases is that the persistent library does not directly provide joins. However, we can use Esqueleto, a bare-bones type-safe EDSL for SQL queries, with persistent serialization to write type-safe SQL queries. It's unlikely that you want to use persistent by itself with SQL, so let's use and review them together. We're using persistent, version 2.14.5.1, persistent PostgreSQL, and Esqueleto version 3.5.10.1, all published in 2023. Additionally, we'll use experimental style, which will become the new default in Esqueleto 4. We'll also use unleaft.io core, monad logger, MTL, time, and exceptions. The library requires a few additional extensions: data kinds, JDTs, type families, and undecidable instances. And last note, it's not very important, but we assume that you've seen the part on postgresql-simple, which covers the same topics but in slower pace. The database persistent PostgreSQL module provides various ways to connect to Postgres with and without connection pool. First, we need the lib pq connection string, which looks something like this. We construct this string from all the hard-coded stuff in the module we've seen before. And then we create the pool and run actions on it using with PostgreSQL pool, and pass in the connection string and actions to be executed. We use lift SQL persist and pool to run an action or a transaction on a pool. We added an alias for simplicity and consistency. And finally, we run with standard out login or no logging, depending on the use case, and appropriate login for our application or environment. The run standard out login is gonna show the SQL queries that gets executed. Okay, but how do we define these tables? Persistent library takes care of creating and matching Haskell data types and persist entity instances. We just need to declare the entities by passing them to make persist once. For example, this is how we're gonna declare the product. We specify the label, which is a text, description, which is maybe text. We specify the label is unique, and derive equals and show for our data types. For Haskell usage, the persist lowercase states that some table, like product category, corresponds to the SQL table, like product underscore category. And product is going to be product category, and so on. We also specify defaults, for example, for created and modified times, and connect the IDs to relevant IDs. For example, product ID in warehouse corresponds to product ID of the product. Even though it's not encouraged, we can always execute raw SQL. For example, we can truncate tables with raw execute and the SQL that we've seen before. What is this SQL persist t with m and unit? Let's say it's something that can be executed with run with pool, we've seen above, and returns the unit. And the m here has monad.io capabilities. Because we've done all the groundworks, we use records and inserts right away. No tuples, no boilerplate. That's it. We say insert and the data we want to insert. Persistent is really concise when it comes to inserts. Note that insert returns the ID and insert menu returns multiple IDs. We can use lift.io to execute IO operations like printing inside SQL persist t because of monad.io m constraint. The first insert gives us back one ID, and the second insert gives us back multiple IDs. Querying data is the part where Esqueleto comes in. First query takes a label and returns a list of product entities. It returns entity instead of just product value because an entity is a combination of database ID and a value. This is experimental syntax which mimics SQL. We use the type applications extensions to make the table explicit. We say table product. We use the overloaded record.dot extensions to select the fields or column values, such as label. We use the equals operator to check for equality, and value to lift Haskell values such as label, text, into the SQL query land. Note that there are other alternatives to this field projections. Instead of overloaded record.dot, you can use view operator if you're familiar with lenses, or overloaded labels, examples of which we're going to see with other libraries. Together with where, we can use in operator to select multiple labels. This time we use val list instead of just val to leave a list of labels. And as expected, when we run the first query with specific label, we get the relevant product back. And when we ask for kit number 1 or kit number 2, we get only one back because that's the only one we have in the database. We've been kind of using transactions all this time. Everything that occurs in a single call to lift SQL persistent and pool, and other versions with and without pooling runs in the single transaction. As a reminder, each single one is going to be a transaction. We have to deal with exceptions. This time, we're going to handle exceptions, any kind of some exception, but we're not going to do anything. We just make sure that we catch the exception, roll back the transaction, and don't propagate the error. In the real code, this should probably be more explicit than just returning units. Also note that we are passing the current time explicitly. In general, we want to split the queries into transactions and catch exceptions on each transactions. And we're gonna dive deeper into the error handling in the error section. Querying with joins is the part where experimental syntax comes in handy. The on clauses are attached directly to the relevant joins. The on clause lambda has all the available tables in it. Only the tables we have already joined are in scope. We use this operator to pattern match against the joined tables. In this case, we have warehouse table and product table. In second case, we don't care about warehouse table anymore, so we can use underscore placeholder to ignore it or ignore multiple previous references. Everything else should be pretty much self-explanatory. We get the data from the warehouse, join it with product, using product IDs, a couple of outer joins to get the categories out, filter out based on the past quantity, lift it using val, and at the end we return a tuple with all the fields we care about and run the query using the given quantity, which gives us back a tuple for the given listing, which generates following query. It is still possible to write type check queries that fail at runtime, but most kinds of typical SQL errors are caught as compile time errors. Sometimes mistakes in queries will result in error messages that refer to library internals. For example, you might see persistence, unique, read backend, something, persistent field, something internal SQL expression, different backends, transformers, and so on. This takes some time to get used to. Help the type inference, and it will help you. And nobody's safe from actual runtime SQL errors. For example, if we violate the uniqueness constraint, we'll get back an error saying that duplicate key value violates unique constraint with a label and the value as details. Note that we use the exceptions package to handle exceptions. We use monad catch constraint on M because this is not an IO. We don't use the exceptions from control exceptions as we did before in postgresql-simple because we don't want to be limited to IO. We use catch from monad catch to add a handler to the action. In this case, we catch some exception and print it back. Don't return anything, doesn't matter, just an example. Persistent is well documented as part of the ESOT book, and Esqueleto has good README and docs. The catch is that you have to keep an eye on multiple packages simultaneously. On top of that, currently Esqueleto supports legacy and experimental syntax, and you have to be aware that some tutorials and examples use less safe legacy syntax or even mix of both. But the good news is the compiler will generally warn you if you're on the wrong path, but you still have to be cautious. Persistent can automatically create tables and do migrations. However, the book discourages that. Using automated database migration is only recommended in development environments. Allowing your application to modify your database in a production environment is very strongly discouraged. You should consider persistent with Esqueleto if you mainly have a lot of simple queries, tired of writing raw SQL, but want moderately more type-safe and composable SQL. The persistent is a very generalized library, which means that you should be comfortable with using abstractions. And you should be familiar with MTL, monad logger, lifting, unlifting IO, and so on. Most kinds of errors committed when writing SQL are caught as compile time errors, although it's possible to write type-checked Esqueleto queries that fail at runtime. And if you look around the web, some tutorials and comparisons might say that Esqueleto joins might lead to runtime errors. But don't worry, this refers to legacy syntax. Just use new/experimental syntax. Okay, are you tired of SQL and template Haskell? Beam is highly general library for accessing any kind of database with Haskell. Beam makes extensive use of GC generic mechanism, no template Haskell. First, install Beam core and Beam Postgres. Then add a few additional extensions, JDTs and type families. Beam Postgres is built on top of postgresql-simple, which is used for connection management, transaction support, serialization, and deserialization. So we assume that you've seen the part on postgres-simple we've done before. When we use Beam, we use postgresql-simple straight away. We use withConnect function, supply it a connection info, and then pass it all the operations we wanted to perform, and withConnect gonna take care of the connection, opening and closing it at the end. Let's look at the definition of the product table. Product T is a Beam table. All Beam tables need to implement the beamable type class, derived via generics, and the table type class, which we'll talk about soon. Product is generic enough because we want to represent both the Haskell type and the entity. For example, when in the code we need to use product, and so later, for example, when we say the function returns product, it's actually product T of identity that it returns. We specify all the columns, we say which types are they optional or not through using maybes, and we also derive an instance for show if we need to show our products. The library suggests also using another type alias for product ID for the primary key of our table, but we don't use it in the tutorial, so it's just here for illustration purposes. The table instance declares the types of primary keys for the table and the functions that extract them. Note that this product ID from here is different from this product ID. For details, see Beam tutorial, which does way better job at explaining what's happening here. All the other tables look pretty much the same. The only interesting bit is the foreign keys, or like referencing other primary keys, for example, product ID and category ID in product category table, because here we use primary key of something instead of just specifying columns as we did before. And after we define all the table, we define the schema. Warehouse DB needs to define all the tables, product category, and warehouse. It also needs to derive an instance of the database, and note that we don't need to hardcode Postgres. It could be generic, but I kept it like this for friendly error messages. If you don't have an existing database, you might get away with only using default DB settings as the database settings. Beam can guess a lot about the tables if we follow their conventions. But in our case, we need to override a few generated table fields. Remember that foreign keys that we have, product ID and category ID, Beam adds a suffix with 2 underscores to it, which means that when we have a record with product ID and we try to use it in a query, the generated query will try to use the column product ID __ID, which is Probably fine if you don't have existing database and you just generate stuffs and you don't care. But in our case, we have an existing database, so we have to override product category and warehouse tables and explicitly tell them what kind of name we want. And we just need to help type inference a bit in the second case because the product ID appears twice. See Beam default for more information on defaults and conventions. So how do we modify data? For raw queries, we can use postgresql-simple. We've seen this before. We use execute function, pass it a connection, raw SQL, and ignore the results because we don't care about them. Let's insert some products. We construct the statement using insert function, which accepts a table and values. We use insert values function to supply concrete values. In this case, we have to specify IDs ourselves because it expects the concrete Haskell values. Run insert runs the statement in monad beam, and run beam PostgreSQL executes this using the given connection, which gives us an IO. Alternatively, we can use run beam PostgreSQL debug, pass it a putStringLine function, and see what SQL queries get executed. Run insert does not return anything. No affected rows, no IDs, nothing. When we want some confirmation back, we can use run insert returning list. In this case, we also use insert expressions instead of insert values to insert arbitrary SQL expressions. In this case, we pass default and ask the database to give us default IDs. Insert products is boring because we don't know what we inserted, and when we insert categories, what we inserted and what kind of IDs were created. Instead of talking about queue monads or monad beam, let's look at examples. First query solve the products. The important bits here is that we build a query first, then we pass it to select, run this in monad beam using run select family functions, which in this case returning list or alternatively returning one and so on. And at the end, we execute this using run beam Postgres on a specific connection. Okay, let's look at another example. To build a query, we use all to introduce all entries of a table, in this case, product table. We use it together with a guard to filter the results by checking label equality, similar to what we've seen before. And then we return label and the description of what we found. In this case, we return a list, but there's only one element that matches this concrete label. Filter is built on top of guard, allows us to use the in clause. We check in that the given label is one of the labels. Note that we use while to lift Haskell values into SQL query length once again. This time we don't use do notation, we use a different style of creating selects. You can use whatever style you prefer. Either way, we're gonna get the product back together with ID, label, and description. We use postgresql-simple for transactions as well. We've seen this before with transaction and connection, and everything that happens inside is a transaction. In case of errors, everything's gonna be rolled back, the error is gonna be rethrown if it's not caught, and so on. The interesting things here is that we have not seen before is that we use just to lift optional values and use them with insert expression. And we also use pk to get the primary key out of these entities that we already inserted. And we also use current timestamp function to ask for corresponding SQL function. Let's move to the more interesting part. There are various ways to get data from multiple tables using Beam. For example, we can use related to get all entries of the given table referenced by the given primary key, and left join to introduce a table using the left join. In case of related, we specify the table and the primary key, and in case of left join, we specify the table and compare the keys. In the latter case, we also use just to leave the optional key, which generates the following query, which is similar to what we're writing by hand. Alternatively, we can use the many-to-many construct to fetch sides of a many-to-many relationship. First, we build the relationship where we specify the database and two tables, and we specify what is the table that's mapping stuff together and the IDs from each one. And when we build the select query, we use the relationship, pass it the entities for products and categories, the ones that we got using related with warehouses and all the categories. Beam does what it does, which in this case generates a following query, quite similar to what we've seen before. It's not possible to write an invalid SQL query, but this comes at a cost. Compile time errors. For example, once we forgot to pass a parameter, and this resulted in this kind of error, which is there is mismatch of a type, but the type needs some time to get used to. Runtime SQL errors are still there, re-exported from postgresql-simple. You can review the relevant error sections if you need a reminder, but this is the gist of it. Violating the constraint results in duplicate key value violates unique constraint error. Beam has you covered. It comes with an overview, quick start guide, tutorial, user guide, and package docs. And spoiler alert, Beam is likely the best documented library reviewed in this tutorial. The Beam Migrate package provides a migration framework. It's a tool that can generate a Beam schema from pre-existing database, manage migration for several production databases, automatically generate migrations between two schema, and much more. Beam states that if the query compiles, it will generate proper code. Beam uses a GHC Haskell type system and nothing else, no template Haskell. You don't have to write raw SQL or SQL-like code. After defining some boilerplate, you write and compose queries in straightforward Haskell style and get valid SQL. Regarding complexity, let the types do the talking. Okay, what if we did something quite similar but quite different? Squeal is a type-safe embedding of PostgreSQL in Haskell, which means that Squeal embeds both SQL terms and SQL types into Haskell at the term level and type level respectively. This leads to a very high level of type safety. Install Squeal PostgreSQL and generics SOP, which is the library which the Squeal uses for generic encodings of Haskell tuples and records. Enable data kinds, JDTs, and overloaded labels extension. It's not very important, but we assume that you've seen the part on postgresql-simple, which covers the same topics but in a slower pace. We pass libpq connection string we've seen before to with connection, and then we chain together all the operation we want to do on this connection. We can also use a connection pool using create connection pool and use a pool with using connection pool instead of just a connection. First, we need to define table columns and constraints. Def means that default is available for inserts and updates. No def means that it's unavailable. We specify the nullability of columns with not null and null. Specify the type for each column. And we use primary key to specify the constraint. This type operator that we see here and here, we use it to pair up a symbol, like description, with the schema type, constraint, column types, and so on. We use this operator to specify the constraint as well as optionality. All the other tables look quite similar, with additional foreign keys here and there, which specify the constraint. You can see the wrapper yourself if you want to see the rest of the boilerplate. Then we define the schema, which means saying the name of the table, passing the constraint and the columns, constraint columns, constraint columns. And at the end, we retype with the schema. When it comes to data, we use generics to convert between Haskell and PostgreSQL values. Take, for example, basic product, which has a label and a description. We derive a GHC generic, and then we derive SOP generic and has data type info. Both of these instances allow us to encode and decode this data type. We can use raw statements if we want. Manipulation represents update, insert, and delete statements. And unsafe manipulation creates unsafe manipulation out of the SQL string. And we use execute to execute the statement. This statement is either manipulation, as we see here, or a query that can be run using monad PQ. Here we use concrete PQ, which allows us to specify the schema changes from DB to DB in this case, which is not very useful. When the schema does not change, we can use monad PQ constraint with just one schema. And at the end, it all becomes an IO when we run it with connection. Okay, let's insert something. We use manipulation and insert into to construct an insert. We pass a table, in this case it's product, using overloaded labels. And what to insert? Values describe a single n-ry product where we have to match all the columns. We construct this n-ry product using this operator. We can use default value for ID and set the rest using relevant parameters. For example, parameter 1 is going to become label, parameter 2 is going to become description, and so on. So when we get the statement, we have to execute it. This time we use execute prepared to run a statement that returns nothing, takes an input. This function prepares the statement and then runs it on each element, in this case for two products. Insert into with underscore is a specialized version of insert into with onConflict do arrays with defaults for onConflict and returning class. The full version allows us to specify what to do in case of conflict and what to return. For example, we can use it to return the created ID. Note that we have to use only and from only because we cannot use primitive types because they don't have named labels that the library relies on. If we try to omit it, we're going to get an error. Also for this insert, we can use execute prepared without underscore because we want to return a list of results. And this result is something we need to unpack. We can use get rows to get all rows from this result. Alternatively, we can get one row or maybe row and so on. If we print it, we get the list of rows where each row is just an ID wrapped in only. To retrieve data, we also write statements. This time we use query and select underscore. The first query returns all the product from the table. And note that we use an explicit type here. Once again, we cannot return tuples or primitive types because they don't have named fields. When you want to return something new, you need to define a new data type and derive squeal's type classes. If you try to use tuples or primitive types, you're gonna get a compilation error. So the query is simple. We get select from the table and we ask for specific fields and then put them together. So I have to execute the queries, get the rows, and see that we get back the results as expected. We can also narrow down the results using where, pass it a parameter, in this case a label, and check for equality for label. This statement takes only text, and this time we use execute params to pass the parameter into the statement and get back the kid number 1. We can also use the in clause to filter out the results and get specific labels. Note, if we omit the type of the query, we have to specify the return type at least. Otherwise, the query is too ambiguous for the compiler to figure out. If we execute the queries, get the rows, and print it, we get back one of the kids. We can wrap the computation in transactionally to get the transaction behavior. In case of exceptions, it rolls back the transaction and rethrows the exception. We'll talk about errors later. It's all the logic and boilerplate we've seen before. The only interesting bit here is that we use now function for created and modified timestamps. For the joins, we use inner join and left outer join to join the tables. Compare product IDs, compare categories IDs, filter out based on the quantity parameter, and so on. This generates the following query. If you forget or mistype anything, most of the time the error messages are rarely simple. Sometimes they're overwhelmed, for example, by dropping the whole table schema in the error. Sometimes they leak and show that there is SOP generic implementation and usage underneath. And sometimes they really leak. But the nice thing is when it comes to runtime SQL errors, the library provides a convenient squeal exception for exceptions that can be thrown by squeal and a nice API built on top of exceptions. For example, we can use catch squeal to catch specific squeal errors and nothing else. So we can catch and do whatever we want with specific errors. The library comes with quick start and core concepts handbook. It also comes with a migration module to safely change the schema of the database over time. They support linear, pure or impure, one-way or refinable migrations. So in summary, Squeal is another type-safe Postgres library not suitable for beginners. You should be comfortable with working on the type level, reading generic related errors, and so on. The library uses generic encodings, generic SOP, for record tuples, which keeps getting into the error messages. Okay, what if we did something quite similar but quite different? Opaleye is an SQL generating DSL targeting PostgreSQL. It allows PostgreSQL queries to be written within Haskell in a type-safe and composable fashion. Install opaleye and product profunctors, which is used under the hood. Also, opaleye is built on top of postgresql-simple, which is used for connection management, transaction support, serialization, and deserialization. We assume that you've seen this part from the beginning of the video. So to establish the connection, we use postgresql-simple right away. Here's a reminder. With connect, connection info, pass all the stuff, get the connection, do the rest. We define a table using table function. We specify table name and type of fields. Table takes write fields and view fields. For example, the first table field ID is auto-generated, so it's optional on write. So we use maybe field here, but it's always there on view and read. This P5 and all the other P's is a tiny glue function from product profunctors. The number corresponds to the tuple arity, 1, 2, 3, 4, 5, or the number of columns. We don't need to know more than that. Table field function infers a required or an optional field depending on the write type. We'll cover this product ID part just a bit later. We can also use records instead of tuples. For example, take this product. This product tick type is polymorphic in all its fields. We'll use product together with this product type in normal code and product field for writing and reading when we interact with the database. Because the product ID is optional, we have to distinguish between product field write and product field, but in some cases you can just reuse one product field. Note that we prefix the field names because we'll have some derivable code that cannot handle duplicate record fields. We also indicate nullable fields with field nullable, which will be converted into maybe when executed. We need some type class instances, which we can get with template Haskell. And if you'd rather write this by hand, you can go to this module, data profactor product th, and see how to do it by yourself. And then we define the table. Note that instead of p with some n, or p of 3, we use p product that was generated here with template Haskell. And the rest is similar to the first example we've seen with using tuples. Now let's talk about this product ID. The library's basic tutorial suggests using new types for IDs. Similar to declaring the product, we declare the polymorphic version, the versions that we're going to use with Haskell, and the versions that we use to interact with database. See the repo for the rest of the boilerplate. Once again, for raw queries, we use postgresql-simple right away, execute connection query. Otherwise, we create insert by using insert. We specify the table, rows to be inserted, conflict handling strategy, and what to return. In this case, we return product IDs using our returning. We pass a lambda that from the product field gets the product ID. And the result is a list of product IDs. Note that we convert the optional field to nullables and passing product ID as nothing. And then we run the insert with run insert and get back new product IDs. Alternatively, if we want to return the number of affected rows, we can use rcount instead of r returning that we used before. We run it the same way and get back the 3. Basic select is simple. We use select table, specify the table, and get back the product field. And then we run it with run select, which converts a record of opaleye fields, for example product field, into a list of records of Haskell values, in this case product. And we have to specify the return type to help type inference. Otherwise the product profunctors are not happy. We can also select specific fields and narrow down the results. We use where to filter the rows and equals operator to compare for equality. We can also return tuples and use in to pass multiple labels. When we run this, we get a label and optional description, as well as just a label, respectively. We use postgresql-simple for transactions. We use with transaction, connection, insert the product, get the product ID back, insert the category, get the category ID back, insert the mapping using the product ID and category ID, insert the warehouse listing using the product ID, the quantity, and nothing for default fields. Note that we can use show SQL to print selects and see what SQL queries get executed. The library provides a couple of APIs for joins. They recommend using where directly for inner joins and optional for left-right joins, which gives us something like this. Select warehouse table, select product table, then the category and product category tables are optional because those are outer joins. All the filtering and where clauses. Then we convert the optional fields like category label and return the result, which gives us a following query. To be honest, I'm still not 100% sure it's proper way to do it because there are no examples, but it compiles and returns what expected. The quantity, the label, optional description, and optional category. And the query itself doesn't have too many joins, so I think it's okay. Once again, type safety and query validation equal compilation errors. But because there isn't much type level magic, we only need to help compiler with type inference time to time. And it's largely about input and return types anyways, not intermediate internal library structure. Take this list of products as an example. This is probably something you want to see in the code anyways. And yes, if you remove it, profunctors show up. Runtime SQL errors again from postgresql-simple. You can review the relevant error section if you need a reminder. There are a couple of basic tutorials in the repo and a couple of external ones. One thing to keep in mind, in some cases the library provides multiple ways of doing things. For example, left joins using optional versus deprecated left joins, or monadic versus arrow syntax. And documentation tutorials can do it one way or even deprecated way. So you have to keep this in mind. The library assumes that database already exists, no support for creating tables and databases or migrations. The library allows us to define tables and write type-safe Postgres queries using Haskell code. The library uses product profunctors and type classes, both only come up in copy-pastable boilerplate and when you underspecify the return types. No deep knowledge required. What if we build on top of that? Relate is a Haskell library for interacting with PostgreSQL databases, which aims to be concise, inferable, and familiar. For the database connection, instead of postgresql-simple, Relate uses hasql. We install Relate and we already have hasql and hasql transaction. We bring back type families extension. And in case you have not already, we need duplicate record fields. The latter is required to disambiguate the record fields when working with insert, updates, and deletes. And we assume that you've seen the parts on postgresql-simple, hasql, and opaleye. To connect to the database, we use hasql. Here's a reminder how to get the connection. acquire, settings, all the hard-coded stuff, either back. Don't do this in production. We get the connection and then we can proceed. First, we describe the structural mappings of the tables. Take for instance product. We define fields with column and derive a relatable instance. We also define a new type for product IDs with a few instances like db equals db type and so on. And then we derive show for product. It doesn't matter what it is, just imagine deriving show. After we define that, we describe a table schema for each table. The relevant product schema looks like this. Name of the table, the schema, the columns, where we map ID to ID, label to label, description to description. And if this looks repetitive, we can use some generics machinery to get that information from relatable we just defined. For example, let's do this with category table. We can use names from label, pass it the category name, and generate a table schema, where every column name corresponds exactly to the name of the field, like we've seen before, ID, ID, label, label, and so on. Alternatively, we can use names from labels with and modify stuff as we want. For raw queries, we can use hasql. Here's a reminder, we have our raw SQL, we create a statement, pass in the encoders and decoders, then we make a session out of that statement, and then we run the session on the connection. And the result is going to be either query error or some result, in this case it's unit. Otherwise, we can create insert. This is pretty much what we've seen in opaleye insert, the table, the rows, the conflict handling strategy, and what to return. In this case, we abort in case of conflict. We return the ID using the projection. We use unsafe default for SQL default. Lit to turn Haskell values into expressions, null for nothing. Construct a query out of the given rows. Note that unsafe default is named unsafe for a reason. We'll talk about this later, but see the documentation for details. Insert of insert creates a statement, and we run it like any other hasql statement, using run, passing all the parameters, and the connection. If we want to return the number of affected rows, we can use number of rows affected instead of projection, and get back the number of rows we inserted. We build a select statement using query. We select all rows from a table using each, and turn or run the query into statement using select. And once again, we run the statement. We can select specific fields and narrow down the results. We use where to filter the rows, the equality operator to compare for equality, and we can also use in for the in clause. Note that the order of parameter is different from the one in the previous library. The first select returns the label and description, and this third one returns just one label. We use hasql for transactions. We run using a transaction with specified configuration on some connection, where the transaction statements are insert the product, returns the ID, insert the category, returns the ID, lift this product IDs and categories ID into mapping, which we have to do this way because the statement can return multiple IDs and inserts take multiple rows, so we can have multiple mappings instead of one. And same for listing. Instead of trying to extract the ID, pass a list of inserts once and pass a list of inserts twice. Note that we can use show query to print SQL queries that will be executed. Relate doesn't have a specific join operation. We use where or filter to filter the results, and optional to do what other joins do. We extract each joins into a specialized function to make the code cleaner, according to the relate tutorial. For example, inner join is taking all the products and filtering out where IDs match. The other two functions look quite similar, but then the usage is a bit different. We use optional and traverse maybe table to account for the partiality of queries. Because the result of optional or outer join is maybe table, the second time we use traverse maybe table to get the second outer join. And then we use maybe table to deal with maybe table. In our case, we have optional category label. And both where and filter are alternative ways to write where clauses. And the generated query, which looks similar to the relevant opaleye query in the previous section. On top of type safety, according to the docs, Relate aims to have excellent and predictable type inference. And they deliver. Type inference rarely needs any guidance, and the compilation errors are quite good. Although it's possible to introduce runtime errors by using unsafe operations like unsafe default, the name is explicit, it's well documented and has proper alternatives. Runtime errors come from hasql, all error reporting is explicit and is represented using either. As a reminder, violating the constraint is going to return a familiar error. Relate comes with Getting Started tutorial, concepts documentation, cookbook, and good API docs, which would have been one of the best coverages But unfortunately, some basic concepts like running selects or constructing inserts are not valid anymore. Also, you have to keep in mind hasql and all of its documentation. Relate also assumes that a database already exists, no supporting for creating tables or in databases or migrations. Relate allows us to write type-safe Postgres queries using concise, inferable, and familiar Haskell code. It's built on top of opaleye and hasql, and you have to be somewhat familiar with the latter. Okay, what if we did something quite similar but quite different? Selda is a Haskell library for interacting with SQL-based relational databases, PostgresQL or SQLite. The library was inspired by Link and opaleye. Install Selda, we're using 0520 released in 2022, and Selda PostgresQL. Enable overloaded labels, create connection info via pg connection info, pass all the stuff, and use it with PostgresQL. And note that we're not gonna pass the connection to every single operation as we did in some previous cases. First, we declare normal, in air quotes, types and derive SQL row. For example, for product, we define ID, label, maybe description, and product ID. Then we use table function to declare a table. Table name, we specify constraints by linking selectors, using overloaded labels, and the definition. We use auto primary for auto incrementing primary keys, primary for regular primary keys, and foreign keys for foreign keys. See the repository for the rest of the boilerplate. We can use raw statement from database selda unsafe to execute raw queries. The selda m is an alias for selda t of IO. Selda t is a selda computation, a concrete implementation of monad selda, which is selda SQL capabilities. At the end, running it with PostgreSQL becomes an IO. To insert data, we can use insert with an underscore that doesn't return anything, insert that returns the number of inserted rows, and insert with pk that returns the primary key of the last inserted row. For the product ID, we use insert with pk, and I'm gonna get ID for this one. In the second case, we use insert, and we're gonna get 3 back because it inserts 3 categories. We also use def when we want to use a default value, which is the case with IDs. We can get all the rows from the given table using select. The result is gonna be a query that returns some row, and we execute query with query. Somehow here, Selda didn't want to read back or parse the IDs, it just inserted it. It says that the row ID column with non-int value. If we change the type here from ID product to int32, for example, the select works, but then the insert and the auto primary stuff does not work anymore. So let's ignore this for now, because the other queries work fine. We can reuse the same select, but then select specific fields and narrow down the results. We use exclamation point with selectors to extract a column, restrict to filter the rows, and equal to compare for equality. A result is an inductive tuple. It's one or more values separated by this data constructor. The return type is a query and is parameterized over scope parameter t, which ensures that queries are always well scoped, but we don't have to worry about it right now. We can also use isin to filter, and note that we don't have to be explicit about the return type or the type of the result. To use transactions, we use transaction. And that's pretty much it. We insert with primary key, get the ID back, insert with primary key, get ID back. Insert the mapping using new IDs, insert the warehouse list using ID, def for default values, def for default values, and that's it. Note that we can use compile from database selda debug to print SQL queries that will be executed. We use restricts and left join to query with joins. We use question mark to extract column from a nullable row, and the rest should look familiar. And this is the generated query. While the TypeScript query is nice and safe, Haskell's type errors can be a bit daunting, even under the best circumstances. In practice, type inference rarely needed any guidance and the compilation errors were relatively clear. The only problem we encountered was the mismatch of ID and SQL's int32. All selda functions may throw selda error. So when we have something like a duplicate key violation, we get a selda error. Selda comes with simple overview, an example, and a tutorial. The library also comes with a migration module for upgrading a table from one schema to another. Overall, selda allows us to write type-safe queries in linear and natural way. Depending on your experience and situation, you might be able to use selda m straight away, or you might need to get familiar with MTL, exceptions, lifting, unlifting IO, and so on. At some point, I just ran out of steam and didn't have the energy to make these things work. I didn't manage to connect to the database using PostgreSQL type. I didn't manage to build hasql relation record and groundhog with GC 945. Neither had releases this year. Also, there are HDBC and Postgres libpq. You might have noticed the libpq connection string we've used here and there. All of these sound fun, but we had enough for now. Maybe we'll revisit and extend later. Okay, big question. So which PostgreSQL library should I use with Haskell? I cannot tell you which library to use. I don't know myself, but I can share the questions that you and your team should consider. Do you want to write raw SQL queries or query builder? Or use some sort of ORM? Do you want to learn a new DSL? How type safe do you want to be? How readable or optimizable the generated query should be? Do you need any bells and whistles like built-in connection pools or migrations? How comfortable are you with Haskell and type level? This complexity is something you can afford. Do you need to be database agnostic? And so on. All this is just the tip of the iceberg. We have not talked about any specific features, performance, compilation speed, and spoiler alert, generics, template Haskell, and type families don't come for free. We are not really at the point where people care to compare for performance, but you don't know unless you measure. If this is something that concerns you, feel free to explore and get some community karma on top of it. Another great contribution opportunity is documentation and tutorials, especially if you have a favorite library and want to convince others to consider it. Wait, is it actually bad that we have so many libraries?